Welcome back. Today, we're going to learn to speak the language of EMC engineers. It's something you'll use every single day. We're diving deep into decibels and all those common units you're going to see constantly. This comes straight from section 1.5 of our source material, so let's get into it.
So just take a look at this number. In EMC, the electric fields we measure can be as tiny as 1 microvolt per meter or as huge as 200 volts per meter. That's a dynamic range of 200 million to 1. That is just wild. That's more than 8 orders of magnitude.
So the big question is, how on earth are we supposed to work with numbers that are that far apart? I mean, without our calculators just giving up or our brains completely melting. Seriously, trying to do mental math across 8 orders of magnitude is a total nightmare. There has to be a better way, right?
And of course there is. The solution is to compress this insane range using logarithms. And this is where the mighty decibel, or dB for short, comes in to save the day. It takes these wild numbers and brings them into a scale that we can actually work with.
Okay, so let's think of this next part as learning the basic grammar of the decibel language. Once you really get these core rules down, everything else just kind of clicks into place. And trust me, you'll be speaking like a pro in no time.
And here's a fun little tidbit. The decibel wasn't even invented for EMC. It actually came from the old telephone industry. And it makes sense, because our ears perceive sound logarithmically, not linearly. So this whole system was a perfect fit for describing audio and noise, way before we ever started applying it to RF signals.
All right, this right here is the #1 rule of decibel grammar. You absolutely have to memorize this. When you're talking about power, measured in watts, you use a multiplier of 10. When you're talking about voltage or current, you use a multiplier of 20. That's it. This is the foundation for everything else.
Okay, so you're probably asking, why? Why the different numbers? Is it just some random rule somebody made up that we all have to follow? Nope. There's actually a perfectly simple reason for it. It all boils down to super basic circuit math. From Ohm's law, that power is proportional to voltage squared. Remember P equals V squared over R? Well, that little squared part, that's the key to this whole thing.
So, watch what happens when we translate this relationship into the world of decibels. We just take the logarithm of both sides. So the log of power is now proportional to the log of voltage squared. And here's the beautiful part. It's a core property of logarithms. That little exponent, the squared term, it doesn't just stay up there. It actually comes down in front as a multiplier, and that too multiplies the original 10 we use for power, turning it into the 20 we use for voltage. See? It's not magic, it's just math. All right, so we've got the grammar down. Now it's time to build our vocabulary. You see, a raw decibel is just a ratio, which is great for things like amplifier gain or cable loss. But to talk about actual measurements in the real world, we need to turn these ratios into absolute units. And the way we do that is by pegging the decibel to a known reference value. A raw dB is kind of just floating out there. It doesn't mean much on its own. So instead of just saying 10 dB, we say 10 dB relative to something. And that gives it a concrete, absolute meaning. And here they are, the 3 most important vocabulary words you are going to use every single day. For voltage, our gold standard is the dB microvolt, or dB mu-V, which is referenced to 1 microvolt. For electric fields flying through the air, it's the dB microvolt per meter. And for power, the universal standard is dBm, which is referenced to 1 times milliwatt. And pay attention to that. It's micro for voltage, but milli for power. So why do we go through all this trouble? Well, here comes the payoff. This is the part where decibels stop feeling like a chore and start feeling like a genuine superpower that's going to make your life way easier. Look at this. Because we're now in the logarithmic domain, all that nasty multiplication just disappears. It becomes simple addition. So figuring out an amplifier's output isn't input power times gain anymore. It's just input power in dBm plus the gain in dB. How much easier is that? And division? Forget about it. If a cable has some loss, you don't divide, you just subtract the loss in dB. This makes calculating what's happening in an entire system incredibly fast and, intuitive. Okay, now for the single most important, practical, real-world shortcut you will ever learn as an EMC engineer. If you work with test equipment, what's coming next will save you a ridiculous amount of time in the lab. Here's the secret. In the EMC world,
Pretty much everything, spectrum analyzers, signal generators, antennas, you name it, is designed around a standard 50 ohm impedance. The entire industry basically agreed on this, and that simple fact unlocks a really elegant relationship between power and voltage. And here it is, the golden rule. In a 50 ohm system, if you want to convert power in dBm to voltage in dBm UV, you just add 107. That's it. That's the whole thing. Burn this equation into your brain. dBm UV equals 107 plus dBm.
Let's see how this works in real life. Let's say we have a signal source putting out -30 dBm. That signal goes through a cable that has 4.5 dB of loss. So what's the power we receive? Simple subtraction. -30 minus 4.5 is -34.5 dBm. Easy. Now, what's the voltage at our 50 ohm analyzer? We just use the golden rule. 107 plus -34.5 gives us 72.5 dB mu. Done. No messy formulas, just adding and subtracting.
But what if you're out in the field and you don't even have a calculator on you, and you just need to get a quick ballpark estimate? Well, guess what? The Decibel system has your back there too. You can get surprisingly close with just a little mental math.
Yeah, the trick is to just remember a few of these key building blocks. You don't need to memorize the whole table. For voltage, know that a factor of 2 is about 6 dB, and a factor of 10 is exactly 20 dB. For power, a factor of 2 is 3 dB, and 10 is 10 dB. If you remember just those, you can combine them to estimate almost anything right in your head.
All right, so let's recap the absolute essentials. First, decibels are our tool for compressing massive number ranges. Second, remember the grammar. It's 10 log for power, 20 log for voltage and current. Third, the magic of decibels is that they turn multiplication into addition and division into subtraction. And finally, in our 50 ohm world, the magic number 107 is your best friend.
So there you have it. You've just learned the fundamental language of electromagnetic compatibility. And this isn't just some abstract theory. These are the tools that will let you quantify, understand, and actually solve real-world interference problems. So the only question left is, now that you're fluent, what are you going to go out and measure? What mysteries are you finally going to understand?